This is Introduction to Statistical Learning, Chapter 10, and we're dealing with neural networks in this chapter. Although this question is more of a zoomed-in picture of some of what's going on, so you'd be forgiven if you didn't see the immediate connection. Okay, so we're going to be looking at the softmax function, which is defined right here and is sometimes used in neural networks, as we'll hopefully see as we go on through these questions. And so we're given two different expressions of the softmax function. So here we have one, and then we have the other. And so we're meant to go and show that if we add a constant, and you'll see what this means here, but if we add a constant to the ZL terms, in other words, these guys right here, in equation 1013, that it doesn't affect the outcome of the model. So the softmax functions are, as an output, telling us the probability of a certain class, that the outcome is a certain class M, given the data X. And we'll see that when we modify this a little bit by adding a constant to each value, we don't change the expression. In other words, it'll simplify and just kind of cancel itself out. And then we'll also show for the same thing, where now instead of using Z, we're adding a coefficient to the beta coefficients in the model, right? So 413 is just expanded 1013 here. Okay, and then it's going to tell us that this shows that the softmax function is over-parametrized. However, regularization and stochastic gradient descent, which is what SGD here is, typically constrain the solution so that this is not a problem. And I'll say a little bit of something about that because, that comment kind of comes out of nowhere a little bit. So, okay, so first we will start with 1013. Okay, so we have our equation here, and again we're just going to add a constant to each ZL. So you notice that Z everywhere gets its own little constant. This is technically ZM up here, but ZM is just one of the ZLs from down here, right? So that's how the softmax function works. It says it's this piece of everything divided by everything. So ZM is one of the ZLs, if that was a little bit confusing for you. But as you go through here, so we added a C to the ZM as well as down here, and then that can be written as just putting another E to the C, right? That's how exponents work. If I add if I have this additive power, well, that's the same thing as multiplying E, the same base E to the to those respective exponents. And now in the denominator, that E to the C is common for each of the E to the Z L's, so we can pull outside of the summation, and then so you notice that the E to the C cancels, and we're left with the same expression as what we started. Okay, there we go. And then the same trick happens down here for 413, the expanded version here. So we have our initial expression, and then to each one of these beta coefficients, I'm going to add its own C value, right? So beta naught here gets C naught, beta 1 gets C1, and that same set of coefficients is being added in the denominator terms. Okay. Well, then we use that same trick where we take each of these C naught values, okay, and we put them in their own E, right, up here, and we do that for both the top and bottom. And because the C to the E to the doesn't depend on the coefficients, right? It's not indexed by these coefficients here. We can just pull it out. And then we have that same thing where we just cancel the top and bottom, and we're left with the same expression. Okay, so that's that. But then the question, like I said, goes on to say that this implies some things, namely over-parametrization, but that we don't need to worry about it in certain contexts. And so I thought I would just say a few things about it. This is not a dissertation on over-parametrization, but you can read through it if you want. But here's the highlight. So So over-parameterization just simply means that different parameter values can lead to the same model outcomes. Okay, and we demonstrated that here because first we had we had a model that gave us this, and then we changed all of the parameters, in this case z, or down here the betas, by adding a constant to each of them, right? And in so doing, we changed the parameter values, but nevertheless, we saw that it simplified to the exact same expression, right? So that really kind of is the definition of over-parameterization. And we demonstrated by adding that constant. Okay, so we get over-parameterization basically when we are trying to estimate more parameters than we have degrees of freedom. Okay, and that's kind of a if you're just confronted with that statement, that's kind of a weird thing. But as kind of an analogy, I mean, it's kind of an example, but it's also kind of an analogy here. It's a little bit like trying to solve x1 plus x2 equals 10. Okay, well, this is, we can think about this as being over-parameterized because we're trying to estimate two quantities, two unknown values here. That's what a parameter is. It's something you're trying to estimate. I've been calling it x1, x2 here, and then calling it x and y down here. Sorry about that. I'll fix that. But we can't really do this, and the reason we can't do this is because whatever x1 is, there's some x2 value out there that will make their sum equal 10, right? If I move x1 up a little bit, x2 could just go down a little bit, and we get 10. And so there's just, the solution space is infinite. One thing that we could do, though, is to constrain x1 and x2, right? Well, one way that we could constrain x1 and x2 is if I just said x1 was equal to, say, 4. Well, then that would mean that x2, or y, as I've switched to calling it here, would have to be 6. Or I could say that x1 is somewhere in the range of, say, 3 to 6. Well, then that means that the other variable would also have a constrained range, right? So if we add constraints to these parameters, then we can reduce the solution space, and so we're constraining the solution space and kind of working towards a solution to over-parameterization in the first place, right? And there's a lot of methods that do this. So in like Bayesian analysis, this is one of the roles of the prior, right? The prior is constraining the solution space. Okay, and so if you're familiar with what priors are, that should make sense. But priors basically tell your model, don't look everywhere. Look primarily in this space of probability space. Okay, and so that's a form of constraint. And so consequently, you can usually get away with over-parameterizing Bayesian models. Well, I mean, are you really over-parameterizing it if you are then constraining them? I don't really know what the right language here is, but hopefully you kind of see what I'm saying. Another way that you can do this is with regularization methods such as lasso, which we've learned earlier in this book, and so on and so forth. So that's just kind of a little spiel about stochastic, or I'm sorry, about over-parameterization. And one more thing to say about it is that over-parameterization itself is not always a problem because when we are just worried about the predictions of the model, well, notice that over-parameterization is kind of defined by different parameter values giving you the same model outcome. And so if we're just worried about the overall prediction of the model, then it's probably not a big deal a lot of times. However, in a lot of different types of analysis, particularly regression analysis, where we are trying to interpret the coefficients, right? So if we have a coefficient for x and we're trying to predict y, well, we might interpret that as, depending on the system, the effect of x on y, right? So for instance, it could be the height of your mother, the height of your father, and as predictor variables, and then your height as the outcome. And we want to know what's the effect of your father's genetics on your height. Well, I mean, in this case, we are concerned with the coefficient, right? And so in those types of situations, now over-parameterization can be a problem, or is a problem, because, again, we can get a lot of different parameter values, but we don't want a lot of, we want a sensible parameter value, not one that resides somewhere in infinite solution space. Okay, I've kind of yapped enough here, so we'll call that good.